Alright, welcome back. Just to follow up from this video to recap a couple of points. Symmetric versus asymmetric encryption. Symmetric encryption, there's one key that is shared. Also known as private key encryption, but on the exam I'll call it symmetric encryption. It is probably the fastest type of encryption. Now, anytime you encrypt a thing, that introduces overheads. If you're encrypting as you're transmitting information, that's going to slow down the transmission of information. When you're encrypting and unencrypting, you're making your CPU work harder, which is again going to slow things down. So encryption does slow the whole process down. Symmetric encryption is the fastest type of encryption, but you do have to share a key. You can't just send the key, clear text in the same channel that you're going to send the encrypted message. That's just not safe. So you have to send it out of band, is what I would call his version of meeting in the park and swapping envelopes, or doing it over a phone call or a text or some other channel besides the medium that you're going to transmit over. So some popular encryption protocols include DES, triple DES, which was 3 times as strong and 3 times as slow as regular DES. And then AES is a popular one. Don't even worry about what these initialisms stand for. AES, let's see, in 468, if you did the wireless site survey, which you don't have to do this go around, you would see that AES is the encryption protocol used for Wi-Fi on campus. If you think of PSK mode in 802.11, something we talked about in 468, WPA2 in PSK mode is symmetric encryption. Now in enterprise mode, it's asymmetric encryption. But let's see, number 2, asymmetric encryption. You've got to have two keys. One's private, one's public, and RSA is a popular protocol used for asymmetric encryption. I think it used to be open source, and then EMC bought them, and then Dell bought EMC. So this is not anything open source. It is proprietary at this point, to the best of my knowledge. Now the only downside to asymmetric encryption is there is more overhead, kind of administrative overhead, because you've got to keep up with a bunch of keys, a bunch of different keys for every conversation. And it's a little slower than symmetric encryption. The same point that applies to the length of passwords applies to key length, which is size matters. There's strength in length. Long is strong. However you want to remember this, but the number of bits, the size of the encryption key, is what's going to stop most brute force attacks, which we'll talk about. Keep in mind that the crypto system itself, the protocol you're using, like AES or whatever you're using, is not a secret. All of these encryption protocols are publicly known. It's just your private key that's a secret. So that's why you've got to keep it secret. The problem for end users is they see a key just like they see a password, that if they forget it, they can just have it reset. There is no way to reset a key. Let me repeat that for the back row. There's no way to reset a key. If you forget the key, you're hosed. This is the number one reason why we don't use encryption across the board for everybody, just because end users are going to forget their key and then they're hosed. Just a little mathematical example of depending on the key length, it's not a mathematical linear increase. It's not even geometric. It's exponential in terms of the more bits you add to the key length, the longer amount of time it would take to crack, to the point where it's not feasible. I do have an example of a brute force attack, but this one's really kind of out of date because an iPad won't let you do this anymore. But it is a good example of just showing how a brute force attack might work, where it's a simple enough code to write to try every combination of every every number, letter, character, starting with one character, do them all, then 2 characters, do them all, 3 characters, do them all, and eventually you'll get in. Obviously, with iPads and other devices, it'll add a delay on every failed attempt, which is really going to slow down the process to keep you from just pop every single time. But other systems do allow brute force attacks, which is a big vulnerability in the system. Now, asymmetric encryption is typically part of a larger system, information system, if you will, called PKI, or Public Key Infrastructure, which includes a number of elements. PKI is a system to provide authentication that you are who you say you are, integrity, the message hasn't changed, privacy because it's encrypted, confidentiality if you will, authorization by the organization, and non-repudiation. Non-repudiation is the interesting one. Some students have trouble with this word. To non-repudiate something means you can't deny that you sent the message. Why can't you deny it? Because so for audit trail purposes, for accountability purposes, if you get a message from my email, tjax@siue.edu, and furthermore it's encrypted with my private key, you know it was me, or that obviously my key got compromised. But it is a good way to, as much as we can, ensure accountability. Which brings me to a sidebar example. I've got a former student who asked me, he was kind of intrigued with this whole idea of writing old-fashioned letters in the mail, and asked me if I'd be a pen pal with him just to try this experiment. So we were writing letters, handwritten letters, back and forth, and we kept escalating on each other. He would send me a note on a legal pad. I would send him some nice stationery. We kept kind of upping the ante on the formality of our exchanges, and I don't know if I was the first one to maybe add a wax seal, which kind of introduces this idea of non-repudiation into the mix. He went over the top and sent me a couple of FedEx boxes that had a scroll that was encrypted, that had a wax seal on it, and separately, i.e. out of band, he sent the Caesar cipher. I don't know if I have a picture of back here. It's just a circle where different letters are lined with, different letters. You can spin the 2 circles within each other. I'm not including it, so you don't see our encryption scheme that we're using. But he encrypted his message the old-fashioned way, the historical way, and I had to decrypt it. So we were kind of geeking out on the whole security privacy aspect of communication these days, and we kind of agreed that authentication, that you are who you say you are, was probably the wax seal. In fact, you'd have to embed something personal in the wax seal to prove it was you. Integrity of the message is the wax seal was not broken. The privacy is from the encryption, the encoding scheme. Authorization, in this case, didn't really translate because we're authorized to communicate with each other. And then non-repudiation might be the signature. That one I was having some trouble with, but finding an analogy. But this was kind of fun to do with him. This got out of hand. Then I sent him one of those Da Vinci Cryptex cylinders where you have to line up the letters, and this is in response to him sending me a message using invisible ink. It's gotten way out of hand, and he sent me like a jigsaw puzzle box that I had to figure out how to undo. And I think he's got the next one. I don't know what he's got in store for me next, but Dan, I'm scared. Back to our regular content, part of this PKI system, there are a variety of moving parts. An important moving part is the certificate authority, the CA server, the registration authority who issues the certificate. So a digital certificate is you are who you say you are. the certificate directory, the management protocols, the policies and procedures are all part of the PKI system. Part of why we need this whole PKI system is because there's nothing around security that's built into TCP/IP. There's nothing that's built into the operating systems the popular operating systems, at least originally. We're starting to now, but originally there was no security built into Windows or Mac or Linux at all. So we've had to kind of cobble together solutions on top of the operating system level, which is why they're pretty slow. Okay, these digital certificates have to be issued by a certificate authority. Yes, I'm talking about the same certificates like in SSL, TLS, like on a web page that in your browser that has a little padlock icon. It's locked. There's a digital certificate validating that the website is who they say they are. But that only works if you trust the certificate authority, the registration authority. What do we call it? Registration authority. So that if I'm the registration authority, you may or may not trust me. But if it's a big name or a standard name, Google or GoDaddy, or there are a lot of registration authorities. But you can do this on your own system, on your own network, because your Active Directory box can serve as can serve up these certificates. Now, the Active Directory box does not. The Active Directory server is not your CA server, but any Windows server can be set up as a CA server. The Active Directory server then dishes out the certs that are generated by the CA server. To validate the file's origin and integrity, that hasn't changed, and who digitally signed it. Here's what the setup screen looks like. So you set up a server with the role of CA as a standalone CA server. And if you read the documentation from Microsoft, this is what freaks me out about CA boxes. It says when you create that root certificate that Active Directory is going to use to digitally sign everything, you configure this server to be a CA server, you create your one root certificate, and then shut down that server and unplug it. Now, you can never get rid of that server lest it fall into the wrong hands, but the box that you use to create that initial certificate you can't keep it on the network for security reasons. So you have to keep it offline. So the last step in the documentation is shut down the server and unplug it. It's crazy. Encryption gets into crazy stuff. So like I said, SSL TLS is an example of public key encryption. It's maybe the simplest example of public key encryption. Now with this particular protocol, this is only securing web traffic. It's not securing all traffic. So this is why an end-to-end VPN is still better, because this is just encrypting web traffic. But it's better than nothing. If you need a little refresher on what SSL certificates look like, we can watch this real fast. This is a little dorky, but here we go.
Problem. You want to provide your customers with a safe, secure environment on your website. Solution. Get some web security. The web can be an amazing place. In addition to providing products or information to people in your neighborhood, city, or state, you can talk to anyone in the world. However, there are all sorts of bad people out there who would like nothing better than to steal your customers' information and credit card numbers. And if customers don't feel safe on your site, they won't want to do business with you. So set up web security. Let's use Bensel's Pencils as an example. They've registered a domain name, they've had their website designed and hosted, and they're ready to start selling online. They need security to provide their customers with a safe, secure shopping environment. In order to do this, Bensel's must purchase what's known as an SSL certificate. An SSL certificate is a sort of online ID card that assures shoppers Bensel's Pencils is who they say they are. This SSL certificate can be purchased from a web services company who is a certificate authority. They research Bensel's, check their references, and positively determine they are who they claim to be online. In addition to providing identity confirmation, SSL certificates also encrypt any data that flows to and from Bensel's site, keeping it secure from outsiders. Security might be offered by the company that hosts Bensel's website, and if it isn't, they can always use a third party. Now let's say an online shopper named Todd wants to purchase a nice mahogany pencil set. There are basically two computers involved with this transaction: the server hosting Bensel's Pencil's website and the computer Todd is using to shop from. Todd's computer connects to Bensel's website, looks at the SSL certificate, and verifies Bensel's identity with the certificate authority. If everything checks out, the computers form an initial connection called a handshake, during which they'll decide what kind of encryption, or scrambling, they'll use. This agreement is used to establish a secure connection between the two computers called an SSL, or Secure Socket Layer.
Or TLS.
Depending on the certificate that Bensel's purchased, Todd's browser may display a small icon shaped like a lock, a thumbs up, a green browser bar, or some other reassuring symbol when security is in place. Once the computers agree on the method they're going to use, data starts to flow back and forth between them. When data leaves one computer, it's scrambled using the agreed-upon method, and then descrambled when it arrives at the other computer. Now Todd can place his order using a credit card, and no matter who tries to interfere, the order, shipping information, and credit card number go to Bensel's Pencils and nowhere else. So let's review. To create a secure website, you purchase an SSL certificate. This certificate authenticates a business's online identity and creates a unique, scrambled connection to provide online shoppers with a safe, secure environment. If customers feel safe, they'll feel more comfortable doing business with you on the web. Problem solved.
The interesting language there is if customers feel safe. It didn't say they are safe. And this is a big distinction. And as a cybersecurity professional, you want to understand this distinction. Why do we do encryption? The only reason we do encryption is not to keep transmission safe. It's because there are business requirements that dictate that our customers will not buy from us if they do not feel safe. So these are things, this is the theater of the mind that we use to make people feel safe. Does it help? Yes. Is it 100%? No! But let's pause here, and then I'll do a last little video for you.